All right, you guys ready?
Dude, this hit.
Nick's helping me with things.
Possible.
He's cutting metal for me and milling it
Except versus
to make race car go.
wait, no.
You're next.
Dynamic
You're next.
forces 1 and 2. C for push.
Dynamic forces 1 and 2. C versus
That would be
Did you get your keys back?
Nope. Judge.
Okay, how do I check my?
Anybody know where my
You wrote on the bottom for speed.
what?
why.
Anybody know where my keys are?
So they
What?
go over the snow easel.
What? No.
Okay.
Sal says that she had to like recite like.
What is
I
it?
mean, I don't know.
Roll it. Well, I mean, it wouldn't hurt that.
Curveball?
No, I can
Roll it.
Here, I'll knuckle it.
That would definitely roll it.
No.
Yeah.
Oh, it's no fun.
I don't want Mr. Pat throwing chairs at my head.
I would never do that.
I don't
I don't know,
believe
you threatened quite a few times. What'd you say?
All right, you guys ready?
Yeah.
So this is a big moment in physics because you're going to learn how the world works, which is cool.
Let's go.
Well, isn't
Welcome
it
back to
flat?
another
So isn't it all
daily
two-dimensional?
episode.
See my pool ball?
Yeah. Wait,
Now-
which number is it? 4.
So they're all the same color in American pool. The same color is always the same number.
Yes.
So purple, solid purple is 4. Got it?
Sweet.
Okay.
Do you need a volunteer to catch?
No, I got this one. So I'm going to put it on here, and I want you to notice what happens when I do.
Accelerates.
Did it roll?
Yes.
Okay.
No.
Hey, Mr. Pettit, what's that pool when they all have like a red ball and then there's like one other color?
So there's a bunch of red ones and then some other colored ones. That's called Snooker.
Oh.
That's a British pool game, and I will tell you, it is hard. 1, the balls are small. 2, the table is much bigger. And the thing that makes it really hard is in American pool, the pockets look like this.
Right.
Okay?
Oh,
The pockets
is
are
it-
angled.
is
So
it
if I shoot
inward?
this here, it's going to hit and bounce in the hole, right? In snooker, they're rounded.
Oh, so if it,
Which means it's nearly, it doesn't want to bank in. It hits and goes perpendicular. So you got to get it deep in the hole for it to get in there.
so, and you can't hit it with too much power.
It's very challenging.
Jack.
That sounds like a,
Okay, less middle school, more high school, all right?
No, I'm.
Right, I got you. I got you.
hey, that's a good day to wear that too.
Yeah.
Yeah,
All right,
right?
hey,
I picked
I
this
wonder
around.
what
Oh,
school
that's
Jack's going to.
Opening day.
Any idea?
Listen, man. Go
Simon.
Tigers.
Oh, we're doing Tigers.
Go Tigers.
Go Tigers.
Ready?
Dude, when do they play?
Watch.
Guys are going without.
Today. At what time?
Can you see it roll?
Yes.
Yeah.
Okay. What we're going to do is we're going to try to draw the forces on the ball to see why it's rolling. See, rolling is a whole new ball game. Okay? I'll tell you what I mean.
Okay.
I'll tell you what I mean.
Oh my God, like the Tigers ball game.
Oh, what a circle.
Jack, you're
Oh, I
so
thought that
funny.
was, I thought that was intentional, bro.
Definitely was not.
You're so funny.
Wow, just gonna be rude to me like that.
Oh, my bad. Sorry, Mr. Bean.
You stabbed me.
Mr. Bean, I'm sorry.
Mr. Who?
That's Mr. Bean. Jack, do the thing.
So,
Do the thing.
let's talk about rolling. Okay? So we have a wheel. Okay? Let's say this wheel is rolling along the ground. All right? I would like to know where it's moving the fastest.
Bro.
Whoa.
Where is it moving the fastest?
It's just
Like,
on a
its
flat
velocity is
surface.
the highest?
Right on the outside of the.
Oh, wait.
Oh,
Wait, on the
yeah.
ball?
On the ball.
Not like it.
So this could be a tire, right? This could be a tire or a ball. It doesn't matter. We're looking at a side view of it. Where is it moving the fastest to the right? Where is it moving the fastest to the right?
Right.
To make it easy, I'll give you multiple choice. Is it moving the fastest at the top, the middle, the bottom, or, secret answer D, it's moving the same speed everywhere? Check your answer, or check your neighbor now. Where is it moving the fastest?
Secret answer C. Secret answer D.
Go with secret answer.
Woman, since it's moving to the right.
It's all like,
Or angular copy.
That's a great question.
That's against.
That's how I feel every day. It's all like,
Why?
force is not a thing.
All right, you ready?
so it's,
He's gonna accept.
science is.
I know.
It's all God.
It's all good. Mr. Pettit, I might have to challenge.
I was
you on
told
the
that by
circle
somebody.
drawing.
The ball is being torqued
God is the.
clockwise, and so that part is being pushed down the ramp.
So rolling is a cool thing because it's a combination of both translational motion and rotational motion. It's a cool combination of both of these things.
Wait, rolling is like.
Rolling is a combination of both of these things because the wheel is actually moving to the right, but it's also rotating clockwise.
Just to the
Right.
right.
Does that make sense?
Right.
Yeah.
Yeah.
You guys with me on that? So if I look at the translational velocity, okay? If I look at the translational velocity, that's the linear velocity. We'll do that one in blue, or no, in green. Okay? The center of mass is moving to the right at speed v. Is that cool? The top is moving to the right at speed v. And the bottom is moving to the right at speed v. Because it's all one object, it's moving to the right. Okay?
And those are the same velocity in train.
Yeah, so the whole thing is moving to the right. Okay? But it's also rotating, isn't it? Which way is it rotating? Clockwise or counterclockwise?
Clockwise.
Okay? If it's rolling this way, it's rotating clockwise, true? So that any given moment, I can put in the velocity, okay? I could put in the tangential velocity on the wheel, yes? So for example, if I look at this thing as it rotates, if I look at this back moment right here, what direction is the tangential velocity at this point? It's up, correct? You with me?
Yeah.
Which way is it here?
Down.
Down, okay? Here, this is the center, so this doesn't have any of that tangential velocity, true? So up here, what do I know?
There's more velocity.
It's to the right, correct? But what way is it down here?
To the left.
It's to the left.
Sweet.
So if I add these together, right? If I add these together, what do I end up with?
More
Zero.
velocity up.
Here,
Oh, yeah, up there.
the velocity is 2v, correct? In the middle, the velocity is v, and what do we know about the velocity at the bottom?
Zero.
It's 0.
So when a wheel, the point where the wheel's touching the ground has zero velocity?
It's not moving relative to the ground.
But only for that one
That,
spot,
that like
which is.
super, like.
For the instant, yeah.
that is-
Yeah.
Do you know what a cycloid is?
Yes, I do.
So, yeah, it's just the point, if you put a point on the circle and
Mhm.
you trace its circumference as it rolls, you'll see at the bottom, it's.
I'll do it. I'll show you. So this is actually really interesting. So, John Lorenzo said, like, look, man, just draw it up. No problem.
You need to get on those wrist circles to make them smaller.
The thing does it for me.
But don't you want to show off?
No.
No,
It'll stop in a second.
it's the hydraulics.
Hey, did we talk about this?
That was at 9 o'clock at night, so roughly.
All right. So this is really cool because this is the wheel at 3 different moments in time. Is that cool? So I'm gonna look at the top of my wheel. The top of my wheel, and then as it rotates, okay? Okay? Is that cool? So as the wheel rotates, it goes like this, which is super cool. Oh, I missed it. So, and then of course over here we do the same thing going backward. So if we watch just one point on the wheel, we see that it actually, here it's moving down, here it's actually moving back and to the left a little bit, true? So it hits the ground here, and at this moment, it switches from down motion to up motion,
Which means 0.
right? It switches from down motion to up motion, which means it has to come to a stop. So at this moment, the place where the wheel is in contact with the ground has 0 velocity. Yeah?
So why is the translational V and the rotational V equal to each other?
That's actually a great question. So I think that that is a necessary condition for rolling without slipping. If it were slipping, they could be different.
Okay.
Okay?
Traction.
I think it actually comes from the fact that this has to be 0 here, which gives you the fact that because we know this is 0, that that has to equal this one.
Okay.
Does that make sense?
What would the line in between each dot, would it look like a cusp? Would it look like a wave? Like you drew like a line between, not necessarily a line, but like you drew between each dot.
Let's see.
Wilson Stott thinks it's the cusp. Step out of
You can close the door, I don't care. I don't know why.
So I've got my essay written.
Really?
And I've been working on it for about.
You have your essay
So
written?
now I'm going to show you how I use Grammarly to.
Oh, I think I've seen that video. Oh, wait. Oh, never mind.
It's gonna play the same note again.
Sorry.
Did you guys see it?
Yeah. Oh, that's sweet.
Does that make sense? So when we watch that part, you can see what's happening here is it goes from down to up, correct? And so, I mean, right before its velocity was straight down, right after its velocity is straight up, there's no horizontals, right? And so this shape traced out by it's called a cycloid. Isn't that cool?
So, since it's on a, if we did this like when it was on a ramp, would the arc just be a little longer?
Maybe. I mean, not really. It's just the same. So this is our concept of rolling. If you look in the, there's a cool picture in the textbook, okay, of all of this. By the way, there's a cycloid picture too. But there's a really cool picture in the textbook on 297. We'll look at it later. It shows it super blurry on top and super in focus at the bottom, and then kind of medium in the middle. Why is that?
Because velocity at the top is.
Because it's going so fast at the top, so it's super blurry, but at the bottom it's not moving at all, so it's totally in focus. So this is our concept for rolling, okay? This is our concept of rolling, and let's see if we can't, okay? Now that we have this, oh, that does not sound good. Think Mrs. Burns okay up there? So I'm gonna take my ball. I'm gonna put it on my ramp. Is that cool?
Yep.
All right, got my ball, I'm gonna put it on my ramp. I wanna know what are the forces on the ball. Check your neighbor, yeah. All right, what are the forces on the ball?
Normal force. Normal force on D. And this is going to be one of our picture force diagrams.
Now, is the ball a rigid object free to rotate?
Wheels out friction.
Yes, it is, which means that we need to draw the forces at the point of contact on the object, just like we did yesterday. Okay? So tell me one thing you know for sure is pulling or pushing on the ball.
And
Okay, I'm gonna do them I'll do them in. Is the earth pulling it down? So we can say that the force from the earth is drawn at the center of mass. I'm okay with that. Everybody's a winner there. Cool? Is that good?
Yeah.
Are there some other forces you would like to suggest? Force normal? All right. Where is the force normal applied to the ball?
Right at the surface of the ramp.
So this is a weird moment because it's here and it goes through the center of mass.
why is that?
Because we have to apply the force at the location of contact with the thing that's doing the pushing and pulling. Because the ramp is touching the ball, that's where we draw the force from.
But is that the case for like